Okay, so hello everybody. Thank you for the kind introduction. My name is Lomazov. I'm a Untitled student, and today I'm going to talk to you about a scalable method of verifying and characterizing quantum computers. And the concept will be understood shortly. So let's start with a few basic examples. One can take 1 qubit, for example, and start it with the 0 state, apply a Hadamard gate. All of you know what will happen. The 0 state goes to the 0 plus 1 state. But once we take a real quantum computer, consists of only 1 qubit, this is what we get. Okay, so not exactly what we expected, but fine, let's continue. Let's consider this example where we have a Hadamard gate with a CNOT. And again, starting with the 0, 0 state, we anticipate that it will go to the 0, 0 plus 1, 1 state. Okay, what do we get in practice? We get in practice this. Not only that we get non-equal weights for the 0 and 1, we also get states that we did not anticipate on getting. The last example, I know it's not really clear. The 4 boxes are identical, and each box is a sequence of x, y, and z. And doing the math in your head on a piece of paper, you see that x times y times z is proportional to the identity. Multiplying them 4 times gives you, in this specific case, exactly the identity, so taking 0 to 0. But still, we get some residue of things that we did not anticipate on getting. By the way, these small and simple simulations were ran on the free trial that you can do on IBM's quantum computers that are accessible for everybody. So, okay, so this is the concept of a verification, okay? We know that something needs to happen. We can simulate it, not simulate it, I'm sorry, but you can pass it through a real quantum computer and see if it matches, okay? Can we do this if we have more than 1 or 2 or 3 qubits? The answer is no. Why not? Because the hardness of calculating, of simulating a quantum computer on a classical device grows exponentially with the number of qubits. This is what we all know. We need a lot of memory, a lot of time, and we don't have that. And this poses a problem. And how can one overcome this despite the exponential growth? Okay, so this is what we're going to talk about today, a method which will be not exponential. Okay, so let's start by generalizing the unitary evolution of an isolated system. All of you know that if we have a psi, a quantum state, it goes through a quantum channel and goes to u times psi through what time step or a iteration step in the quantum computer. Fine, but we don't have isolated systems in reality. Okay, but we can consider what's not isolated and what can happen. So one can consider the trivial things that we know that can happen to qubits, which is bit flips or phase flips or combinations of the two. Okay, this exact property of a specific type of noise can be characterized by this no longer deterministic but random channel, which takes psi to different psis with different probabilities. Okay, fine. Let's take it one step further and talk about the same thing, but in the context of density matrices, which is a generalization of the psi, of the cat state. So the unitary channel, which will denote always from now on by epsilon, large epsilon, can be written as this, u rho u minus 1. Okay, fine. One can show that the last example that we gave for the flips, different kind of flips and combinations, can be written as this quantum channel, which is also called depolarizing channel. Okay, and these are just special cases of something more general that we call Krauss channels. Okay, the most general form of a Krauss channel can be written in this form with some f's. So this thing is called a Krauss channel, and the f's called are Krauss operators, and they satisfy the completeness relation that is written on the right-hand side. Okay, so if we understand and consider the fact that every dynamic, every action of a quantum system and a quantum computer is defined by some Klaus channel in the most general sense, one would like to study and verify that the quantum computer does indeed does the quantum channel it's supposed to do. So let's learn the quantum channel. Following Eyal Be'eri's, Netanel Lindner, and Itai Avat's works, we start with a steady state. A steady state is a state that can be achieved by taking an initial state, plugging it into the computer, into the quantum computer, getting something. We don't know if it did what it needed to do, but we don't let go. We keep on going. We take the output, put it back, and do it more and more and more times until the input state does not differ from the output state. This is the definition of a steady state. So taking this steady state, denoted by rho, now that it's a steady state, is equal to epsilon of rho, okay? Because it gives the same thing. Doing some, I don't think some tedious manipulation, but we can take the completeness relation. Oh, I need to point it there. Okay. Some manipulation by multiplying by the density matrix rho, which is the steady state, from the right-hand side, from the left-hand side, summing and dividing by 2. Now we have two equations that states rho is equal to something. Okay, so let's equate, move it all to the one side, and we get this. Well, now is gonna be the part where nobody will see it right away how it happened, but we do three things. The first one, we say that these f's, defining the Klaus operators, are local, and we expand them in some base elements ps, which are just Pauli strings. And we multiply everything by some matrix, some observable A, and we trace, okay? As we all know, the right-hand side will stay 0, but we will get this monstrosity. Okay, you don't really need to understand what happens here, because if I take all the trace and all the things that inside the trace, and I just call it K, and this small sum over the small c's, which define the Krauss channel, I just call it big C instead of small c. This is just a linear and homogeneous equation. Okay, so let's see what this linear homogeneous equation can give us, and why is it called scalable method. So remember, solving this equation gives us the quantum channel. Okay? The quantum channel we need to study, the quantum channel that holds noise. Okay? So if we look at the size of the matrix, we see that n is proportional to the number of base elements, which is linear in the system size. In order for this equation to be solvable with a unique solution, we need to take m proportional to n, at least n. One can think about examples when you can take less of it, but it doesn't matter. The point is that the number of elements and the number of and the time that it requires to simulate this K matrix and to solve it is only polynomial in the system size instead of exponential. Okay? So by solving this equation, we can find in polynomial time the Klaus channel and verify if it does what it needs to do. So making this, if this is correct, then we can verify any quantum computer, regardless of how many qubits it has. Not only 1 or 2 or 3, but 10 and 50 and 100. And just to give you a little taste of what this algorithm can practically do, is we consider the very, very specific and trivial noise, which is, by the way, called amplitude damping, okay? Corresponds to spontaneous emission. If we have the one state, it spontaneously decays to the 0 state by emitting a photon. And this corresponds to this quantum channel by these two Klaus operators. And, okay? And the point is that we took here just a single parameter for all the qubits. And this picture just shows us how casually we can, by performing minimization on the k times c with variational principle, find the epsilon. This is the bigger picture. Thank you for listening, and please ask questions.
What about the kernel of K?
What about the kernel of K?
I mean, it probably has many 0 nodes.
Well, the zero modes are less relevant. You want to find only the one solution, which is supposed to be non-trivial, and in most cases it is. And this solution corresponds to the non-trivial Klaus channel.
Anyone else?
Yes.
Not from so you show here that you find a polynomial way to find the channel, right?
Yeah.
And the problem that you showed originally is that you have errors. I mean, does finding the channel actually that you correct these errors or just characterize them?
Just characterizing is just saying, I think that the errors in this device are modeled by this Klaus channel. This is the characterization part. The verification part is the fact that you can find the steady state of this channel, construct this equation, solve it, and find the C's, and the C's tell you what is the Klaus channel. So you can actually know what your quantum computer needs to do once you know the coefficients of the different different elements. There was a question.
If you have some decoherence mechanism that involves something of all the qubits together, have a very complex mechanism, will it still be solvable? I mean, you'll get in the limit you'll get to the same complexity as n squared, n to the time n or something like that. No?
Something that I might forgot to say, that the assumption is that the Fs that build the Klaus channel are spatially contiguous. Okay, so you can take 2 local, so nearest neighbors. You can take 7 local. You can take 100 local. As long as it's not all of your system and it's just part of it, it will still be polynomial in the subsystem size, and you will still be able to solve it efficiently. Again?
It's like having clusters of spin.
You generally look on a subsystem of a larger system. The point of how to stitch them together is somewhat a different point.
Anyone else? Okay, so can I ask a question?
Of course.
Yeah, I want to ask it. So you said at the beginning of the talk that you tried this on the IBM quantum computer, or
Yeah.
maybe you tried it on other systems, I don't know. Have you discovered anything like really interesting?
Well, not yet. For now, our main goal is to being able to find many parameters with ease, and there is a lot of freedom. In fact, I didn't have time, and it was kind of obvious to talk about this graph, but this graph contains a lot of parameters that I chose by myself. For example, the fact that per qubit can get only these 3 types of gates, okay? And the fact that I choose a specific set of observables, and the fact that I randomized with what probability these gates can act upon each qubit. I can change all of that, choose everything different parameters, different operators, different everything, but still the epsilon that I originally implanted should stay the same. So there is a lot of freedom in the ways that you can find it, and we are currently working in optimizing the way to find specific things.
Thank you.
Shai, I want to say one thing.
Please.
You gave a wonderful talk. You
Thank
were
you.
clear and absolutely
Thank
clear.
you. I was nervous for that.
Maybe that's good. All right.
Thank you.